Okay, this is a mechanism problem. So we've got a symmetrical diketone on the left. We're going to treat that with aqueous hydroxide in refluxing condition, under refluxing condition. It's going to boil. It's 100 degrees. It's hot. So symmetrical diketone, aqueous hydroxide at 100 degrees. We get this alpha beta unsaturated ketone. Give me a hit pause, come up with a mechanism for this reaction. Okay, now that you're back, ketones, base, we're making carbon-carbon bonds. That should, so ketones, base, we make carbon-carbon bond formations. We make carbon-carbon bonds. All of this should suggest aldol chemistry. But how does that happen? Okay, so aldols should suggest enolates. Okay, if you want to write, if you're taking notes, hit pause and write that down. Okay, so let's look at the enolates we can make. Again, I mentioned this is symmetrical. This methyl is identical to that methyl. This CH2 is identical to that CH2. And obviously that CH2 is just itself. So I'm going to work on this one over here. We got 3 enolizable protons there and 2 here, and they're obviously not the same, so I've put them in different colors. So hydroxide is going to come in. All right, so if we take a red proton, we're going to get this enolate. If we take a blue proton, we're going to get a blue enolate. Obviously, I'm just talking about the ink. It doesn't. Enolates are usually kind of yellowish, and they have negative charge. Okay. All right, those are the 2 enolates we can get. Now, do either of those help us out? And the answer is yeah. If you look at the red one is the thermodynamic enolate. It's a more substitute. If you draw the resin structure, the carbon-carbon double bond is more substituted. But the cyclization, so we're going to have, right, we're cyclizing the molecule. So one of these atoms has to attack the ketone. If this negative attacks there, we make a 4-membered ring. All right, so we're going to get a 4-membered ring. I haven't drawn this in a while. Let's see if I can actually get this. So that one, so we'd have an O minus method. Is that right? 1, 2, 3, 4, 5, 6. That doesn't seem right. So that, never mind. I put it in the wrong place. O minus method. There we go. That's the 4-membered ring. 4-membered rings aren't terribly stable. There's a lot of ring strain. So this thing just opens right back up, goes here. So the equilibrium in this case very much favors the left. All right, so I'm going to get rid of the red. We're not, the red, deprotonating either of the red protons doesn't get us the product. So what about deprotonating, taking a blue proton off and getting this enolate? Well, now, cyclize, right? Let's put numbers on this. So 1, 2, 3, 4, 5, 6, 7. I highly encourage you guys to do this as you're working these at home. Okay, so this cyclizes, and that's going to give us carbon 1 is going to attack carbon 6. That's a 6-membered ring. So let's say that 1 bonds to 6. Right? Carbon 1 makes a bond to carbon 6. So we've got 2, 3, 4, 5 in between. 2, 3, 4, 5. Carbon 7 still bonded to carbon 6. I don't know why I put that in black, sorry. Carbon 7 is still bonded to carbon 6. So remember, the arrows, the curved arrow of your mechanism will tell you what bonds form and what bonds break. If an atom doesn't have a bond to it, or an arrow to it, right, there's no arrow involving 6 and 7, the electrons between 6 and 7, so that bond stays intact. 3 and 4, nothing happens to them. So for this step, these arrows say carbon 1 bonds to carbon 6, and the pi bond between carbon 6 and the oxygen breaks. All right, so 6 needs an O- on it as well. Now, just put everything that needs to be on there on there. So carbon 2 has a ketone. 3, 4, and 5 are methylenes. That's fine. 7's a methyl. There we go. So that's your aldol, and that should look a lot like this product. You should be able to see this product in that, you should be able to see the product in this intermediate. So now what happens? How do we get there? So that's our first intermediate. That's the aldol addition intermediate. We're in water. So the O- is going to take that proton. Now we get the aldol alcohol product. All right. Now we have to do a dehydration. You guys have done eliminations a lot. In the ketone, you could work this up. Or look, there's no workup given here. I don't say you put this in acid. So did you guys like, oh, let's protonate this? Remember, we're still in hydroxide. Okay, we're under strongly basic conditions. You can't protonate this OH to make it a leaving group. So what has to happen? Hydroxide's going to make another enolate. And this is reversible. But that enolate is a strong base. So at any given moment, right, the equilibrium here favors the left. But you have maybe 1%, maybe 0.1% of these molecules are going to be the enolate. And so when it gets to that enolate, the negative charge on the carbon can kick out hydroxide. And that takes us to our quite stable alpha-beta unsaturated carbonyl. And the water that forms, you're going to get hydroxide out of this, it'll grab a proton somewhere, and that water just blows out the top. So this is an aldol condensation, an intramolecular aldol condensation. Right, so you make an enolate, that enolate then attacks a carbonyl in the same molecule. So really, again, can't emphasize this enough. If you can make a 5 or a 6-membered ring, that usually happens in nature. You see a lot of 5 and 6-membered rings in organic chemistry. So if you have a reaction that can give you a 5 or 6-membered ring, it's very likely that that's going to happen. All right.